In lecture 6, we are going to derive Planck's law from Bose-Einstein statistics. Now, in the previous lecture, we have done application of Fermi-Dirac statistics. Now, in this lecture, which is the last lecture of this module, Statistical Mechanics, we are going to use Bose-Einstein to validate one of the very important law, which is called the Planck's law. Now, Planck's law is connected with black body radiation. So before I explain black body radiation, let me give you an idea about the electromagnetic spectrum. So on your screen, you have the visible region, and this is expressed in terms of wavelength as well as frequency. So from left to right, the wavelength is decreasing and frequency is increasing. So you have the relation that frequency nu is equal to c by lambda, where c is the velocity of light and lambda is wavelength. So you can see that visible, when you decrease, the wavelength decreases, you have the ultraviolet, X-ray and gamma, which means that E is equal to h nu, or energy of electromagnetic waves is inversely proportional to wavelength. So the energy is high in this region and low in this region. Now, what is black body? A body which is, when it is kept at low temperature, it absorbs all wavelength of light, all electromagnetic waves, and when it is taken to a high temperature, it releases different wavelength. So a black body is never 100%. That means that the amount of the amount of light or the wavelength of light it absorbs may not give all the wavelengths, or may not give out or emit all the wavelengths. So taking this example into consideration, if you calculate or plot the energy emitted versus wavelength, we get such kind of plot. Now, why I am considering this example? Because when scientists or physicists try to explain this experimental curve, the experimental curve shows in the x-axis you have wavelength, and in the y-axis you have the energy density, or you can also plot the intensity of the emitted light from the black body. So in this region you have the ultraviolet region, because wavelength is plotted in the x-axis, so ultraviolet light has less wavelength, then comes the visible, then the infrared. So what happens with the increase in wavelength of light, the energy density or the intensity of light increases, reaches to a maximum, and then decreases when black body is kept at different high temperature. In this example you have 3000, 4000, 5000, 6000 Kelvin. So the pattern or the nature of the curve remains the same, but the peak increases with increase of temperature. So physicists try to explain with the available physics. They use thermodynamics, they use the whatever physics that was known to them, they could explain, not the entire curve. And two well-known scientists, two group of scientists, they came forward and they tried to explain. One was Wien. He could explain the increasing part, that means in the lower wavelength region, and Rella and Jean could explain the decreasing part of the curve, that means in the higher wavelength region. But none of this group of scientists could explain the entire curve. So Planck, with her new idea of quantum physics, he could explain this curve, and from there onwards quantum physics was developed, and Planck's law was also developed from this well-known experiment of black body radiation. So what does this Planck's law say? Here U means the energy density, which is energy divided by volume of a black body. Energy is h nu by E is equal to h nu. divided by volume will give you energy density. Nu is here frequency. 8 by h is Planck's constant, c is velocity of light. K is Boltzmann constant, T is temperature. Now the first thing that arises that why we have considered in this lecture Planck's law as an application of Bose-Einstein statistics. Because we are trying or we will derive Planck's law from B statistics. Now there are three available statistics, MB, B and FT. I have shown you in my previous lecture that we studied semiconductors behavior at different temperature from FD statistics. Then why do we choose B statistics to derive Planck's law? Because B statistics deals with photons and black body radiation deals with light, and we all know from quantum physics, even Planck, Einstein, they have proposed that light is are particles which are photons, and for this reason we are going to use B statistics to explain Planck's law. Now let me recap B statistics once again, where F is the distribution function, N is the number of particles, and G is the number of quantum state at every energy level. 1 by e to the power of alpha, alpha is constant, plus beta ei, ei means E1, E2, E3, Ein, energy, different energy levels. Beta is equal to 1 by kT and alpha is constant. So if I want to express now this distribution function in terms of energy, I can write down in this form. So N, what I have done, so if you want to express the number of photons, N means the number of particles, here it is photons. So if I want to express what is the number of particles of photons between E and D, E plus D, then you have to write the number of photons as a function of energy. What I have done, I have taken this G to the other side and everything remains the same. So from here onwards, I have the number of photons from energy E to E plus D, and then for black body there are some assumptions to be taken to modify this distribution function from B statistics. Why the modification has to be done? That I will explain now, but before that let me tell you that the distribution function of Bose-Einstein statistics, Bose-Einstein has taken into consideration while deriving this mathematical form of distribution function that the total number of particles in a system remain conserved or constant. But in black body, as you mentioned, that black body is never 100%, which means the number of photons getting in, that means the different color of wavelength of light getting in, absorbed by the black body and emitted by the black body, they are not same. So number of photons and absorbed and emitted, they are not constant or conserved. For that reason, we have to consider that the number of particles, they have considered, Bose and Einstein have considered number of photons or particles constant. But in our problem is to derive Planck's law. Now Planck's law deals with black body, and in black body it's not conserved. So number of particles is not constant. So that is why I'm writing dn, the change in number of particles, not equal to 0. And because of this reason, alpha, the constant, said to be 0. Here beta is equal to 1 by kt and k is Boltzmann constant. So in the next step you will find that this Bose-Einstein distribution function gets modified for this problem, for the black body problem, where I will take alpha to be 0. So I have taken alpha to be 0, so alpha is made 0, and then I converted this energy in terms of frequency. So what I have done, I have substituted the value of E is equal to h nu. So E is equal to h nu from Einstein's equation. I have expressed this energy in terms of frequency. So the right hand side now changed to frequency. So because h is constant, so I can write that G as a function of frequency. Similarly, number of photons is also a function of frequency. So what I have done, again I repeat, that energy is converted to or transformed to frequency, and we write down the same distribution function after taking alpha to be 0. We write down in the form of frequency. So basically this expression means the number of photons in the frequency range of nu to nu plus du. Now we also know from the phase space lecture that number of quantum states from frequency nu plus du, that is g, is equal to 8 pi v by c cube nu squared du. This expression has been derived and shown in previous lecture in the lecture phase space. So what I am going to do, I am going to substitute this value of number of quantum state in this equation, and what I am going to get, I'm going to get in this form. So I'm writing, I will substitute the value of g nu here. So after substituting the value of g nu, I get 8 pi v nu squared d nu c cube e to the power of h nu kt minus 1. Now in the next step, what I'm going to do, as because Planck has expressed the Planck's law as energy density, so I'm going to transfer or transform this expression after substituting the value of g quantum state into this equation. I'm going to change this number of photons in terms of energy density. So how can I do it? If I say that I have a photon of frequency nu, what will be the energy of that one photon? It will be E is equal to h nu. If I have n number of photons, the energy of that n number of photons will be n into h nu, right? If I say what is the energy density of the n number of photons, so energy n h nu divided by volume will give me energy density. So energy density U is equal to h nu divided by volume into capital N. Capital N is called the number of photons. So what I'm going to do, I'm going to substitute the value of this n, this part here, because n, I will substitute the value of g here and then take this value of n and substitute in this equation, and finally I will arrive that energy density is equal to h nu by v, 8 pi v by c cube into nu square divided by e to the power of h nu by kt minus 1. So this will get cancelled, volume, and finally I'm going to get energy density as U 8 pi h by nu cube by c cube into nu cube e to the power of h nu by kt minus 1. So this means, why do I have d nu? Which means that energy density to be when I have d nu, it means that energy density is calculated from a frequency nu to nu plus d nu. So this is your Planck's law. Energy density is expressed as 8 pi h by c cube into nu cube by e to the power of h nu by kt minus 1. Now with this, we have the last part of this statistic mechanics, where it says that under which condition the Maxwell's the Fermi statistics and Bose-Einstein statistics will reduce to Maxwell's-Boltzmann statistics. As in the first lecture I mentioned that classical statistics means Maxwell's-Boltzmann statistics, and Bose-Einstein statistics and Fermi statistics, they are called the quantum statistics. So what is the meaning of this statement? It means that under which condition, under which physical condition, the Maxwell's-Boltzmann or Fermi statistics will behave as the Fermi statistics and Bose-Einstein statistics will behave as Maxwell's-Boltzmann statistics. So let us give an example. Suppose you have a container containing electron gas. Now under which condition of physical condition this same electron will now behave as Maxwell's-Boltzmann statistics? Under which physical condition? How under which when these electrons, generally electrons will behave as Fermi statistics, but under which condition this will behave as Maxwell's-Boltzmann statistics? Suppose if I have a container containing photons, then under which condition this will behave as Maxwell's-Boltzmann statistics, because photons behave as Bose-Einstein statistics. But what is the condition? Now, before I tell you the condition, let me give you some. Again, I repeat the distribution function formula for each of the three statistics. It is here on the screen. Now, if you just carefully observe that the difference between MB, B and FD, they are almost same with alpha, beta terms and energy terms, but in Maxwell's Boltzmann, you don't have this +1 or -1, but you have -1 in the B statistics and +1 in the FD statistics. And what is beta? Beta is 1 by kt, and alpha, it is a constant. It is basically expressed in terms, if you talk about Bose-Einstein, it is minus mu by kt. If you talk about FD, it is actually minus EF by kt. So these three I can express collectively in this form. The distribution function is equal to number of particles by number of quantum state is equal to 1 by e to the power of alpha plus, now I have substituted the value of beta, ei by kt. So you can break this e to the power of alpha, because it's exponential power, I can break this into e to the power of alpha e to the power of ei by kt after substituting the value of beta. Now plus a delta. Now delta is 0 for Maxwell's Boltzmann statistics. So if you substitute the value of delta 0, this formula now changes to MB. If you substitute the value of -1 as delta, you get the value distribution function for B. If you substitute the value delta as +1, you get the distribution form for FD. So now mathematically speaking, if delta is +1, it is FD. If delta is -1, it is B. Now if I remove this delta, then what does this form will change? It will change to MB, mathematically speaking. So if mathematically, if I change this delta to 0, then obviously this expression will change to MB. So if I have an expression of delta either plus or -1, and by some condition if I prove that delta is neglected, then means delta is 0, that means this expression leads to MB statistics. Now under which condition this delta can be neglected or 0? I can say that delta can be neglected or 0 if this expression is very greater than 1. When does this happen? This happens when temperature is high. When temperature is high, in the sense that alpha is always, in every statistics, alpha is constant, but if you quietly observe the value of alpha, it is inversely proportional to temperature. So for any given temperature, alpha is basically inversely proportional to temperature, and because of that, this expression leads to much greater than 1, and so delta can be neglected. Or in other words, I can say that if this becomes much greater, it's very high value, then this becomes very less. That means if temperature is very high, okay, inversely proportional, then this entire expression becomes very high. As temperature, this expression becomes very high, and the number density, number of particles by number of quantum state, becomes very less. So if I have to finalize this statement, I can say that what is the condition that you have the FD and B reduced to MB. So it is that e to the power of alpha into e to the power of ei by kt, if this expression is much greater than 1, then number density changes, and the delta sign in the previous slide can be neglected, and once it is neglected, from the expression FD and B reduced to MB. So I repeat, when as alpha is inversely proportional to temperature for B and FD, high temperature value leads to low number density, and low number density leads to MB statistics, classical statistics. So if in one word, if I am asked to say that under which physical condition FD or B will lead to MB statistics. I would say that under high temperature and low particle density, the quantum statistics will lead to classical statistics. So now we come to questions from this lecture. We have already done Planck's law from BS statistics, and please, when you derive, assumption is very important, because there we are taking alpha to be 0 because the number of particles, there it is photon, is not constant for black body, so Dn not equal to 0 and alpha is equal to 0. This important assumption has to be taken or written during the derivation of Planck's law from BS statistics. And from the topic that what is the physical condition that tends FD and BE to MB, these two important questions are there from that part. Show that MB or Maxwell-Boltzmann energy distribution is a limited case of B and FD distribution. Hence prove that MB distribution is applicable to rarefied gas, because you know that MB has low density, because as delta tends to 0, this when these FD part or B particles will lead to less number density, which means you are moving to Maxwell-Boltzmann statistic. So Maxwell-Boltzmann particles are less dense, so it is called rarefied gases. So it is from that same topic, the condition that where quantum statistics leads to classical statistics. And another question connected to that, explain why dilute gases obey classical statistics while dense systems follow quantum mechanics. The same answer, that FD statistics and B statistics, they are more dense, the number density is very high compared to classical or MB statistics. So what is the reason? That has already been explained. So here we come to the end of statistical mechanics as well as lecture 6, and again I hope you liked it, and thank you so much.